My name is Max, and I'll be narrating this multimedia session on how water brake absorbers work. First, let me do a quick overview of the basic components. Starting from a suitable pressure and capacity supply, our cold water flows through a load control valve, then, via a flexible hose, to the absorber's inlet. Later I'll explain this hot water gravity drain. The absorber's outer stator housing may be supported by cantilever mounting it to the crankshaft, or on a pair of external pillow block bearings shown now. Either way, the trunnion stator cannot rotate more than a couple of degrees, due to this attached torque arm and load cell linkage. Now, I'll section open everything, allowing us to look through our stator's toroidal pockets, and exposing the opposing pockets in the water brake's rotor. The rotor's shaft mounts in its own bearings, and is what users couple to their test engine. Lastly, we have an RPM pickup, to capture crankshaft speed. Now let's see how it all works. Water brakes are basically very inefficient pumps. They use the engine's power to accelerate a mass of water within the absorber's rotor pockets, but then transfer that kinetic energy by colliding the radially spinning water into the brake's stationary stator walls. The load cell gauge monitors the torque induced from resisting the water's radial motion. During all this churning, friction between the water molecules raises their temperature, shown by our droplet turning red. To prevent boiling, we must constantly drain warm water and replenish it from the cool supply. Let's see it again, but with more detail. Watch as we zoom in on a water droplet at the stator's inlet hose fitting, entering a pocket in our spinning rotor. The engine lugs down, as it must supply power to radially accelerate this extra water mass. Observe how the resulting centrifugal force slings the droplet outward, and that it then follows along the toroidal pocket's curve. Changing our view angle, watch as the next droplet slings out of the rotor, into a stationary stator pocket. Its radial motion abruptly stops as it impacts the fixed stator walls. This lost water momentum becomes a rotational force against the stator, which the torque arm's attached load cell records as engine torque. Note that the droplet's circulatory flow continues smoothly along the pocket's toroidal path. Combined with an RPM reading, we now have everything needed to calculate horsepower. This acceleration and deceleration is a continuously repeating process. It will occur several times per engine revolution, and involve gallons of water per minute, not just this single droplet. Whenever the drains and valves flows are set in equilibrium, the water mass within the brake stays constant, as does the power required to turn it. However, by increasing the inlet flow control valve's opening, the water mass within the absorber will grow, adding more pumping cycles. Notice that this raises the torque load, or lowers the RPM of the driving engine. And, as you would expect, if we reduce the flow, the torque loading of the absorber will decrease again. In closing, I should mention that the specific power capacity of water brakes is extremely impressive, especially considering their relatively low cost. Combined with computer-controlled inlet or outlet valves, they can also be made surprisingly responsive and stable. That's it for now. You may want to watch again, to better understand everything that was going on.